Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 4, Section 2, and we're on Part 4. So today, let's talk about what we did last time. So last time we talked about changes in energy, and if the energy is, more is being more is being absorbed, it is an endothermic reaction, and if more is being given off or released, it is an exothermic reaction. And so as I promised, we're going to talk about this thing called enthalpy. And enthalpy is the energy potential of a chemical reaction, and it is measured in kilojoules per mole. Basically, enthalpy is the change in energy. I'm going to move this back up. So enthalpy is basically the change in energy during a chemical reaction. Enthalpy, change in energy. Everybody got it? Okay, so the energy of the products, so where you end up minus the energy of the reactants, where you started, is your change in enthalpy. So let's say it is a positive change. So if the energy of the products is higher than the energy of the reactants, so where you ended up is higher than where you started, when you subtract those two numbers, you're going to get a positive result. And that means that your energy of the products is higher, which means you gained energy. So when energy is absorbed, remember we call that endothermic. So positive enthalpy means the products gained energy. Energy was absorbed, and the reaction is endothermic. So the opposite is also true. Negative enthalpy means the products lost energy. So that means that the energy of your products is lower than the energy of your reactants. When you subtract the energy of the products, which is a small number, from a bigger number, you get a negative number. And if you lost energy, then it means it was released, which means it was an exothermic reaction. So negative enthalpy means the products lost energy, and it's exothermic. Let's look at an example. So energy going in. So photosynthesis, as we know, energy is absorbed during the chemical reaction. It's like energy is a reactant. So please write this down. Photosynthesis is endothermic, and it requires an input of energy. So photosynthesis is endothermic, and it requires an input of energy. And that energy comes from sunlight. And the opposite of photosynthesis is cellular respiration. So please write cellular respiration is exothermic, energy out, and it releases energy. Again, please write cellular respiration is exothermic, and it releases energy. As we know, we're taking that stored energy in the bonds of glucose, breaking them down in the mitochondria to make ATP, which is usable cell energy. So how do these two processes relate? So in cellular respiration, 2,800,000 joules are absorbed for every 1 mole of glucose that is created. And in cellular respiration, for every 1 mole of glucose that you break down, you get 2,800,000 joules of energy. So the amount that goes in is the same as the amount that comes out. So energy is neither created nor destroyed, because the sunlight came from the surroundings. So the amount of energy absorbed into that chemical reaction came from the sunlight from the surroundings. And then the energy released when your mitochondria is doing cellular respiration is being released into the surroundings, which is your body. So we know, no, it did not disprove the first law of thermodynamics. It followed that. So what is missing in just these equations? Well, we know mixing water and carbon dioxide doesn't make sugar and oxygen because you need an input of energy. Also, you need a catalyst, and a biological catalyst is called an enzyme. So you need enzymes for this to happen. And then just if you mix sugar and oxygen, you don't get water and CO2 because you also need enzymes. Looking at a third example, what is still missing? So a candle burning gives off heat. It is an exothermic reaction. But the candle does not spontaneously light itself, thankfully for us, and no enzymes are needed to start this reaction. We're missing something still. So just like it takes energy to separate two magnets, it's going to take some energy to separate two bonded atoms to start that reaction happening. And what is that beginning energy? It's the activation energy. So please write this down. Activation energy, measured in kilojoules per mole, is the energy needed to start a reaction. So even exothermic reactions, even reactions that give off energy, need an activation energy. So burning gasoline is an exothermic reaction. It gives off a lot of energy, but you need a spark. You need a little flame to ignite the gasoline for that reaction to occur. So we are going to draw a simplified view of this graph. So you're going to have energy on the y-axis, and then as time goes by on the x-axis, and then reactants on the left. It's going to go up a little bit and then down lower for the products. Okay, so let's take another look at this. So you still have the same graph. It hasn't gone away. Activation energy is what we're talking about. And then if you want to write this equation and kind of follow along, that would be helpful. C6H12O6, which is glucose, plus 6O2 yields 6H2O plus 6CO2 plus energy, 2,800,000 joules. Couple questions for you. Is this photosynthesis or cellular respiration? So this is giving off energy. It's starting with glucose and water, glucose and oxygen, so that is cellular respiration. And is this an endothermic or exothermic reaction? Well, it's giving off energy, so it's an exothermic reaction. All right, so we're starting out with the reactants, our C6H12O6 and our 6 oxygens. And then we're ending up with our products, C6H2O plus 6CO2. And the energy released is the difference from the beginning to the end. So please draw this, a line not all the way up to the top, but just where the reactants is, down to the line where the products are, is the energy released. And then the activation energy, please label that. It's from not the whole bottom, but from the top to just where the reactant energy was. That is the activation energy. And that's the energy barrier you have to get over. You got to push things up a little bit of a hill before they will roll down. So how do we get chemical reactions to occur? Well, it depends on the chemical reaction. If it is like a candle burning, you're going to light it with a lighter, and then that will get it started. You get the paraffin, the candle burning. If it is photosynthesis or cellular respiration, you have those catalysts, those biological catalysts, the enzymes, that lower the activation energy and help start a chemical reaction. Okay, that concludes our Chapter 4, Section 2 notes, and we're going to jump in our next video to Section 3 and learn more about some specific types of chemical reactions. I will see you then.